Hello, so in this video we're going to be talking about this thing called chaotic behaviour and strange attractors. These two kind of phenomena that occur, and in order to do that I'm going to sort of introduce it using really the classic example of this thing called chaos theory or chaotic behaviour. Okay, and it's via what we looked at last video, which is the Lorenz equations. Now, if you remember last video, we had these system of equations, and these system of equations basically looked at how, well, specifically it looks at fluid dynamics, so, or generally I should say, it looks at fluid dynamics, so how kind of fluid changes with respect to temperature, okay? So differing temperatures, how fluid changes, but obviously it can be used to predict the weather, okay? Because if you think, we use the example of the Earth, here's our Earth. Okay, just the Earth's surface, section of the Earth's surface, and the Earth's atmosphere is kind of here, so this is the atmosphere, okay, and so obviously it'll be cold, it'll be warmer at the bottom, close to the surface of the Earth, and it'll be colder up towards the top, so we've got this kind of differing in temperature, this difference in temperature, okay, and these equations basically would try and model the air movement based on, the differing temperatures, or the difference in temperatures. So we had these parameters here, which was sigma and b, and we just took them to be 10 and 8/3, because that's what the parameters are found to be on Earth. Okay, they remain the same. And I just sub those back into these equations. If you remember, x corresponded to the intensity, if you like, of the fluid movement, so in this case, the air movement, and sort of that's what we were really interested in, because obviously we're interested in sort of seeing how the air moves over time. Y was just a temperature difference in the sort of horizontal direction, and Z was a temperature difference in the vertical direction. So really the thing which we were interested in is kind of X, how the intensity of air movement changes. And if you remember, we had a parameter which was R, okay, and that was basically just approximating the temperature change. So basically, if we could see how R changed over time, or see how R changed with differing temperatures, I should say, then that's kind of the thing which we're interested in measuring, and then we can use it to then predict and model sort of real life situations. Okay, so we looked at how we could solve these three equations, because obviously up to now we've only sort of solved two nonlinear equations. Now we're sort of solving three at the same time, so it's a really good example of that, and sort of trying to show how you can solve sort of higher linear, sort of higher order terms. So in other words, higher order just means that we've now got three variables instead of two. Okay, so it's just a good example of how to solve a nonlinear ODE. All right, so we showed how to solve it in the last example, but basically now what we want to consider is how x changes over time. So literally just draw the graph of x against t, and this is what we did down here, and this is what's been done for us down here. Okay, so we get this graph out, and we use the initial condition, or the initial points, 5, 5, 5. So in other words, x, so this is x, y, z, so x, y, and z. Yeah, so x, which is the airflow, we just took to be 5. The difference in the y sort of temperature is 5, and the difference in the z temperature, so the vertical temperature or height, is 5. Okay, so these are just the initial points. Now the thing is, what are initial points? I should just kind of mention this. I know I have mentioned it before, but it's applicable to say now. It doesn't take long. Think of a gun being fired. That is kind of our initial condition. The actual firing of the gun is our initial condition. It's the thing which sets something off. Okay, so it's kind of like, we can start anywhere. If we have a graph, we can start anywhere on this graph. So the initial condition will just tell us exactly the point to start at. If you like, it's the gun which is being fired off. It's the thing which sets off kind of the sequence of events. It's the thing which kind of puts us at this place, right? Don't worry too much. The initial point is just the point at the very start, okay? If you like, it's the gun being fired. It's the point at the very start, the origins, if you like, of our solution. And it will also tell us which trajectory we should travel along, the initial point does. All right, so we get this graph up when we put 5, 5, 5. Now, what Lorenz did, these are Lorenz equations. He was the meteorologist who kind of looked at these equations, Lorenz, American. What he basically did is, what happens if we consider a slightly different x value? So when I mean slightly different, I mean slightly different. So by the way, we're considering in both cases r to be 28. We're just fixing r to be 28. What happens if we just change the x value ever so slightly? And I mean ever so slightly. Most people would look at 5 and 5.01 and just think they're so close to each other. Okay, so what would you expect to happen if these two, if you're putting in basically the same points, considering basically the same points, this is a very, very slightly different. 5.01 is very, very slightly different to 5. So what would you expect? Well, you would expect it still to follow this kind of graph, wouldn't you? Because even though you're considering a different point, so if we go back to our initial point example, okay, even though you're considering a point which is slightly off this initial point, we're really, really close to it. So we would expect it to follow this kind of similar behaviour to this graph here. Yeah? Expect it to follow a very, very similar path, even though it's slightly different. You know, slightly different, so we'd expect it to follow a very, very similar path. But look what happens. Yeah? The dotted line, the dashed line, this dashed line, is for this 5.01. Sorry, no, this is for the this one up here. So this dashed line is what we had up here. So this is for 555, this dashed line. But when we put in 5.01, that's when we get the solid curve. Okay, the solid curve corresponds to 5.01 and the dashed line corresponds to 5. Well, it's exactly the same. If we start over here, if we start right at the beginning of time, t equals 0, it's exactly the same. It follows exactly the same curve. Right the way up here, right the way up here. Then when we get to a value which is just above 10, so let's just call it 10, for example. When we get to this point here, all right, so let's call it time equals 10, we suddenly go off on a completely different trajectory. So basically, this slightly different value here, this 5.01, basically means that after a point in time, we end up going on a completely different path. Even though these two numbers are really, really close to each other, 5 is really, really close to 5.01. We would expect it to follow the same curve, or roughly the same curve, but it doesn't. After a point in time, it goes off on a completely different, path altogether. Okay, so Lorenz looked at this, and he went, whoa, this is weird. This is really weird. Okay, and basically, when you try and put it in context of the weather, what this is saying is that we can only predict the weather using these equations. We can only predict the weather up to a finite point in time, so sort of a near point in the future. So we can only predict the weather for the near future. Okay, because these parameter values can vary, obviously in the weather, these parameter values can vary. So we kind of have a range of values that this parameter can take. Kind of, if we look at the weather, we get the data in, and we have basically a range of values that this can take, and we kind of condense it down to a range of values of this, this. And basically what this is saying is, well, look, most people, let's say 5, if we get 5 out, if we get x equals 5 out, let's say that corresponds to rain. So x equals 5 out, that corresponds to rain. Well, up until the near future, we can say definitely what the weather is going to do. Okay, so say, for example, for the next week, we can accurately predict the weather. All right, so say, for example, if 5 corresponds to rain, okay, so for the near future, we can predict that it's going to be raining. Yeah, accurately predict it's going to be raining for like the next week. But then anything beyond that, it's really difficult to predict because, look, any changes, any slight variations, so say, for example, 5 is rain, it could be, this graph could correspond to rain, but then this dash graph could correspond to, I don't know, sun. Brilliant sunshine. So basically, beyond, next week, if we use these equations, what Lorenz is trying to say is, after a point in time, so say like up to a point in time, we can predict the weather accurately, but after a point in time, we can't predict the weather because look, it varies so much. Just with slight variations between 5 and 5.01, these two values vary ever so slightly, but they can have totally different effects for kind of like, say, the next week or the next month. You can't predict the weather accurately beyond a point in time. You can only predict it for the near future. So that's kind of the application of this, or the implication of this, in terms of the weather context. Okay. So now what I'm going to do is I'm going to come on to this thing called strange attractor. Okay. Now it kind of makes sense. Let's look at the two words individually. So attractor actually does make sense in this context. Attractor is just basically, if you're attracted to something, it means that you're drawn into it. Okay, so an attractor is just a set of values, which a system will tend towards. Okay, so that kind of makes sense. If a system is attracted to a set of values, we call that an attractor. And we were looking at, for example, with our nodes. With our equilibrium points with the linear case, if a point is an equilibrium point is called an attractor, if all the trajectories are kind of drawn in towards it, so that's known as an attractor. So attractor kind of makes sense. But this thing called strange, if you can kind of see it, I suppose, but it's less obvious. All right. So this thing called strange basically it corresponds to this fractal behaviour. It corresponds to this thing called a fractal behaviour. Now, what's a fractal? Well, if you've met a fractal before, then you probably will know what it is. But if you haven't, let's just do a very, very quick reminder of what a fractal is. Basically, it means, I'll just tell you what it means. It means, what are you doing? It means infinitely jagged. It means infinitely jagged. Okay, so basically if we have like a jagged graph, something like this, and say it's a fractal, right, there we go, so we've got a fractal, then basically if we zoom in, if it was a smooth graph, we could zoom in and zoom in and zoom in, and eventually after a point in time, so let's say if this was a smooth graph, we could zoom in, and after a point in time, this would become like a straight line, it becomes nice, smooth, straight line. Okay, if we zoom in enough times. But with a fractal, we zoom in and zoom in and zoom in, and it will still be jagged. So we zoom in, and it'll still be jagged. Then we zoom in a bit more, okay, and it'll still be jagged. And in actual fact, we can zoom in an infinite number of times, and it will still be jagged. It will never go smooth. All right? And actually, this is the reason why a fractal can't be differentiated, okay, using ordinary differentiation. You have to use actually this thing called stochastic differentiation, which deals with kind of probabilities, and then you incorporate those probabilities and use things like Ito's lemma and stuff like this. But we can differentiate a fractal, but not using ordinary differentiation. Okay, but basically this is all strange means. It just means it's a fractal. Okay, so a strange attractor. Well, what will that mean? It just means that a set of values will basically tend, or a system will basically tend towards a fractal. Yeah, and if you look up here, you can hopefully see with these graphs that it is kind of a fractal. It is really, really jagged. Okay, and actually, if we zoom in a bit more, I mean, these graphs have actually been computed numerically, so it's not actually a true fractal drawn like this. But if you actually did the maths of it, it does come out as a fractal. So in other words, we zoom in and it will still be jagged. Okay, and that's known as a strange attractor. So basically, a system which tends towards a fractal. Here, and this is an example of a fractal. Okay, so now we're going to talk about this idea of chaotic. So that's strange attractor. Now we're going to talk about this thing called chaotic. And a chaotic behaviour, basically, I mean, we talked about it before. We talked about it up here, okay, where just varying the input values, varying the initial conditions ever so slightly will result in a completely different graph, yeah? Because we expected that because these initial values were really, really the same, ever so slightly different, but they were really could be considered as the same, we'd expect them to follow kind of a very, very similar path, if not the same path. But because these two values are ever so slightly different and it follows a chaotic behaviour, then basically that means that we follow a completely different path. And you can see with this graph in particular, okay, that we have a different graph. With this graph, we kind of go up here a bit. But then whilst we're up here, with the other graph, when this is 5.01, so it's varying ever so slightly, we're down here. So we're down here for 5.01, but then if it's 5, we're up here. So we're completely opposite sides of the equilibrium point. Okay? So completely the opposite sides of the equilibrium point. So basically, chaotic behaviour is highly sensitive. Highly sensitive, what do we mean by that? It just means that it's prone to change. If you're sensitive to something, it means that the smallest change causes, a big change, or very sensitive to small change. You know what sensitive means, don't you? Highly sensitive to initial conditions or initial points. Okay. So even though, and I should really introduce this word called deterministic, just because this is related to it. Deterministic. Basically, all this means is that future behaviour is determined, so in other words governed, by whatever the initial conditions are. Okay, so basically the initial conditions tell you what's going to happen in the future. All right, that's, it's not random. So not random. Deterministic is kind of the opposite of random. Okay, so not random is deterministic. Yeah. So basically, if you wanted to visualize this, imagine firing a gun. So we've got a gun. Okay, we've got a gun. That's a gun. Okay, and we fire a bullet. We fire the gun. Okay, and fairly obviously we aim the gun and it will finish up over here. Okay, so where we aim it to be. But then basically we then fire a second bullet. So our first bullet starts here and it ends up here. But then let's say we fire another bullet, but we move the gun just ever so slightly, you know, by literally a fraction of a millimetre. Fraction of a millimetre. So in actual fact, we're firing it from a slightly different position, but only ever so slightly. You know, well, when we fire a gun, we would expect it to kind of end up in roughly the same point, okay? But actually, what happens just by varying the gun by with chaotic behaviour, just by varying the gun by just a few millimetres, we end up in a completely different place altogether. You end up in a completely different place altogether, and it actually follows a completely different path altogether, just by varying that gun by a few millimetres. So that's kind of an example, a visual example of chaotic behaviour. So we've got strange attractor and chaotic, and I've kind of summarised it down here. So strange attractor just means that a system will tend towards a fractal. All right, and then chaotic is basically the present values determines, if the present value determines the future, but the approximate present value, so just by changing the present value by just ever so slightly, does not approximate the future, or approximately determine the future. Just if you understand my example with this, if you can visualise it, then that's much better. But yeah, maybe that's not the best way of saying it, but if you can make sense of it. So the present determines the future, but the approximate present does not approximately determine the future. Okay, so in other words, if we vary the value ever so slightly, we end up with a different result. Good. I hope I made that a little bit clear. Okay. So now, basically, what Lorenz wanted to look at, so he kind of established this strange attractor where it tends towards a fractal, and chaotic behaviour, where kind of just by varying the initial conditions ever so slightly, we end up with something completely different path. But if you noticed, you know, these both tend towards a strange attractor. Okay, we end up with chaotic behaviour over here. But if you notice, they're exactly the same graphs. So kind of what we would expect up until a point. So up until this point, these two graphs are exactly the same. So these two graphs are exactly the same. Yeah. So just because this is kind of what we expect, you know, we vary it by ever so slightly, so we expect the graphs to follow the same. But then beyond a certain point in time, we end up with totally different graphs. So beyond this point, suddenly we end up with totally different points. So basically what he wanted to look at is, well, for what values R? How does R affect this kind of behaviour, this chaotic behaviour? So what happens as we vary R? So for what values of R do these phenomena happen for? Okay, and this is exactly what he did. I've got it up here. And this is exactly what he did here. Maybe I should just remind you of what we did last time with these Lorenz equations. So I've got x against t. I've got x against t, and I've got my points on. So this is P1, and this is the origin. Then I've got P2 sort of above this kind of equilibrium point. If you think this axis, this t-axis is the equilibrium point. Above the equilibrium point, I've got P2, and below the equilibrium point, I've got P3. Okay, and this kind of corresponds to what we were talking about before with chaotic behaviour. So basically, we're the same up until a point in time. All right, and then beyond that point in time, we follow completely different paths. So we can either go positive or we can go negative. We go this path towards P2 or this path towards P3. Yeah, and if you remember, we worked out sort of different values of R because we ended up with a cubic equation. When we tried to solve our system of equations, we ended up with a cubic equation, and so we just looked at what the different values of R happened. So if you remember, for R less than 1, we were kind of this side of the equilibrium point. We were on the negative side of the x-axis, and we were tending towards our equilibrium point at 0, 0, 0, P1. Then as soon as R equals 1, P2 and P3 came into existence. Right? They actually came into existence at the equilibrium point, but let's just say they came into existence. Just for the visual sake, they came into existence. Just take that. Okay, and then for between 1 and 24.737, so R equals 1 and 24.737, so that's the value of R which falls between these two values. When we put R in, these two, you know, any value between 1 and 24.737 in for R, we basically either head towards P2 or we head towards P3. Okay, and then beyond 24.737, we kind of just carry on sort of away from these points. Okay, so basically, this is what Lorenz was considering. So let's now change R equals 21. So we're now considering in this point here. So in other words, this is the point we're interested in. This is the point where actually we would expect you know, this bifurcation to happen, these two paths to happen. It's a bit like varying the initial condition ever so slightly. So basically said, right, okay, we vary the initial condition and we're considering in this point here. So basically where we're heading towards either P2 or heading towards P3. Okay, so we took R equals 21. And first of all, he took the initial point, the initial condition 380. Okay, so in other words, we made Z0. If you remember, Z was just the vertical difference in temperature. right? And we made 3, 8, 0, so x is 3 and y is 8. So in other words, we're kind of considering along the surface, okay, but we're just kind of considering y movements now. So the y movement, the y difference was 8, yeah? So the horizontal difference in temperature was 8. And if we did this, we pretty much ended up at P3 straight away. Hopefully you can see here, you know, we go up, then we go down, and then we kind of, you know, we end up heading towards or tending towards P3 virtually straight away. You know, pretty quickly we end up heading towards P3. Okay, but then what he did is he looked at, okay, what happens if we have 5, 5, 5? So the same point we had before. This is 5, 5, 5, and this is what we ended up with. But this time we're considering r equals 28. Well, which point does it tend towards? Well, it tends towards P2. Okay, it does play around for a little bit. You know, it sort of is a little bit hyper, kind of is jumping around a little bit, but then it kind of settles down and it basically tends towards P2 for r equals 21. So before we were considering in this region over here with r equals 28, this is this graph over here, we were considering r equals 28, so we're considering over here, okay, and we couldn't really see what happened, but that wasn't kind of what we're looking at there. But now we're considering in this region here, so between, you know, these two values here. And if we get these initial conditions now, we basically settle down, we play around for a little bit, you know, we jump around for a little bit hyper for a little bit, but then kind of fairly quickly, fairly soon after, we head towards P2. All right? But then basically what he does is he uses similar kind of initial conditions, but here where it's 5, so now we're just considering a change in the vertical direction. So here where it was 5, so say if we were here it's 5, now we're considering 10, so in other words we're doubling the vertical direction. So we're starting here and we're ending up over here. So now this is 10, this whole thing in here is 10. Okay, well let's look at what happens. Well look, we're really hyper for a long period of time. So basically we've hit 12 or a little bit beyond 12, and if you look with this graph, we pretty much were tending towards P2 by this point. But look, we're still jumping around. So t equals 24, t equals 36, t equals 48 even, we're still jumping around. And then it changes its mind. So it looks down here when we're at 48, it looks towards, you know, we might be looking to settle down a little bit. But then it changes its mind again. And then finally, after, you know, t equals, what's that, about 80, it then finally starts to head towards P2. Okay, so basically what he said, what he kind of concluded is that as r increases, the duration of kind of mucking around, this kind of hyper behaviour, you know, jumping around a lot, mathematicians call this transient behaviour. Transient behaviour. Okay, this kind of jumping around. As r increases, so r is, remember, roughly proportional to our temperature change. So in other words, we're considering a larger temperature change. So say, for example, so yeah, as r increases, this kind of transient behaviour, this kind of jumping around, this hyper behaviour also increases. So in other words, it takes longer to settle down towards a particular equilibrium point. So as r increases, the transient behaviour, this kind of hyper behaviour, also increases. So what does this mean kind of in the real context of the world? Remember x, you know, the thing which we're looking at is basically looking at how kind of air movement is affected by temperature change. You know, so how hyper air is, you know, it's kind of turbulent air, you know, fluidity of air. Air movements is affected by temperature change. So basically for small temperatures, say for example from 3 degrees C to I don't know, 4 degrees C, shall we say? So a change of temperature by 1, okay? This transient behaviour, so we basically expect it to tend towards a value pretty quickly for small temperature changes. Okay, expect it to tend towards a value for small temperature changes, for kind of small temperature changes which tends towards a particular value. Okay, so it kind of settles down after a little bit of time. But then let's say, for example, if we consider from 3 degrees C to, I don't know, 60 degrees C, that's a really large temperature change, or relatively large temperature change from 3 to 4. All right, so therefore we expect it to kind of jump around and kind of not really tend towards anything for longer. And then finally, you know, for after a long period of time, we would expect it to settle down, okay, to a particular point. So this is kind of what Lorenz was looking at. And this is, you know, but basically the idea is you know, chaotic and strange attractor. I mean, it's interesting to see what values these phenomena occur at. So basically, for larger R values, we kind of see this behaviour occur. So for larger R values, so for larger temperature change, okay, these phenomena occur. Okay, so as we increase R, these phenomena occur. But basically, the idea is that, you know, the main point of this video is kind of to get you to understand strange attractor and chaotic behaviour. Yeah, so in other words, strange attractor, it tends towards a fractal. So kind of lots of jagged, jumpy up and down movements, which is kind of what we were looking at over here. Where is it? This is what we're looking at over here, this kind of fractal behaviour, this jumping around. Yeah. But the chaotic behaviour is basically just saying, if we vary the initial conditions ever so slightly, instead of them following roughly the same path, which is what you would expect, they actually follow completely different paths. So it's very much dependent on the initial conditions. It's deterministic of the initial conditions.